Today, we embark on an exploration of a bold and transformative idea, the quantum electrodynamic brain. Traditionally, neuroscience has relied on classical electromagnetism to explain neural activity, treating neurons as simple electrical conductors. However, emerging research suggests that the electromagnetic properties of the brain may extend equations into the quantum realm. In other words, the brain is traditionally understood through neurochemical and electrical interactions, yet electromagnetic, EM, fields also play a crucial role in neural communication, cognition, and potentially, consciousness. In this presentation, we will trace a journey from classical electromagnetism to electromagnetic, QED, considering the brain as not only an electromagnetic conductor but also an active generator and radiator of electromagnetic waves. We will examine how a full-wave electromagnetic model, rooted in Maxwell's equations and extended into a quantum framework, may offer deeper insights into neural processing, information transmission, and consciousness itself. Let us begin by understanding the full electromagnetic spectrum and its significance in brain function. To understand this paradigm shift, we must first examine the transition from classical static electromagnetism to the dynamic framework of quantum electrodynamics. On this slide, we see a visual representation of the full electromagnetic, EM, spectrum, spanning from low-frequency static fields to optical and high-energy quantum interaction. The brain's electrical activity has been modeled using quasi-static Maxwellian electrodynamics, which describes neuronal currents, membrane potentials, and ionic movements. In this point of view, quasi-static fields governed by Gauss's law and Ampere's law, relevant for resting potentials and slow ionic movement in neurons, and radio and mice governed by Faraday's law and full-wave Maxwell solutions, related to EEG, MEG, and neural oscillations. However, this approach does not fully capture the complex field interactions, wave propagation, and quantum scale effects occurring in the brain. Quantum electrodynamics, the fundamental theory governing light-matter interaction, nuanced picture. In this framework, the brain is not merely a passive conductor but an active participant in quantum electromagnetic interactions, potentially involving biophotons, coherent wave phenomena, and quantum entanglement among neurons. Thus, our goal is to bridge the gap between classical and quantum models, providing a framework for understanding the brain's electromagnetic behavior. Infrared and optical regions consider transition from Maxwellian electrodynamics to quantum electrodynamics, QED, as photons at this scale exhibit wave-particle duality, relevant for biophoton emission in neurons. This transition from static to wave-based to quantum electrodynamics that neural activity extends beyond classical conduction and may involve non-local electromagnetic and quantum interaction. One of the fundamental principles in classical electrodynamics is that any conductive structure immersed in an electromagnetic field interacts with that field. The brain, composed of interconnected neurons with varying conductivity, behaves as a complex electromagnetic conductor. Neurons generate electric fields through ionic currents flowing across membranes, sodium, Na+, potassium, K+, and calcium, Ca2+, ion channels. These moving charges create both electric and magnetic fields, which can extend beyond individual neurons and influence nearby cells. Furthermore, myelinated axons act as waveguides, channeling electromagnetic waves along their dissipation. This property suggests that brain communication may not be limited to neurotransmitters and synaptic transmissions, but may also involve electromagnetic coupling and field-based interactions. To study this phenomenon rigorously, we turn to Maxwell's equations, the cornerstone of classical electromagnetism. The brain's ion-rich intracellular environments behave as a complex conductive medium, where neural currents flow. Membrane potentials store and release charge, behaving as dielectric capacitors in Maxwell's equations. Synaptic current flow induces localized electric fields, affecting nearby neurons. Thus, the brain does not merely generate electrical pulses, it forms a dynamic network, continuously interacting with self-generated fields. Maxwell's equations describe the behavior of electric and magnetic fields, providing a theoretical foundation for understanding the brain's electromagnetic environment. These equations include Gauss's law, which describes how electric charges produce electric fields, Faraday's law, which explains how changing magnetic fields induce electric field law, which relates electric currents to magnetic fields, Gauss's law for magnetism, which states that there are no magnetic monopolies. In the brain, these equations help us model electrical activity, from neuronal action potentials to large-scale brain oscillations seen in EEG and MEG recordings. However, static electromagnetism alone to explain certain experimental findings, such as evanescence wave propagation from neurons and non-local interference pattern in brain medium. This brings us to the need for a full-wave representation. A full-wave model accounts for the propagation, reflection, and absorption of electromagnetic waves in the brain, beyond the simplifications of traditional quasi. This approach includes electromagnetic wave interactions between neurons, field coupling effects beyond local synaptic transmission. To develop an accurate computational framework, we employ a forward model based on Maxwell's equations. This model allows us to predict how electromagnetic waves propagate in the brain, considering factors such as the electric properties of neural tissue, the role of the myelin sheath as a waveguide, the possibility of long-range electromagnetic interactions within neural circuits. A specific adaptation of this model is the Darwin model, which refines Maxwell's equations by eliminating far-field radiation effects, focusing instead on near-field interactions, which are more processing. With this full-wave framework established, we can now explore the brain as not just a conductor, but an active electromagnetic generator and radiator. In this point of brain as an electromagnetic generator and radiator, neural activity is not confined to individual neurons. It generates electromagnetic fields that extend into the surrounding medium. The brain does not just conduct electrical signals, it also radiates electromagnetic waves into its environment. To fully capture the full electromagnetic field of brain activity, we extend our framework into higher-dimensional electrodynamics. In a higher-dimensional representation, electromagnetic fields are not confined to 3D space, but may interact in additional spatial or quantum dimensions. Neural ion transport can be reconsidered as a source of both fields and quantum field interactions. The vector potential method provides an alternative representation that is more suitable for quantum electrodynamic formulations. Ion channels play a fundamental role in this process, acting as dynamic electromagnetic sources. The movement of charged ions across membranes generates both electric and magnetic fields, contribute to the complex electromagnetic environment of the brain. By considering the Lorentz transformation, we can analyze how ion transfer in neural circuits aligns with relativistic electrodynamics. The brain's electromagnetic interactions can be described using the four-vector formalism, where neural currents and fields are components of a higher-dimensional electrodynamic. Additionally, the field tensor formalism allows us to generalize Maxwell's equations into a broader context, providing insights into how ion-driven electric and magnetic fields interact within neural networks. This framework suggests that the electromagnetic activity of the brain is not merely a local phenomenon, but is influenced by relativistic principles, contributing to large-scale coherent interactions across neural structures. Moreover, emerging evidence suggests that biophotons, weak light emissions from neurons, may play a role in neural signaling. These biophotons, potentially entangled through quantum effects, could provide an additional layer of communication beyond classical electrical. This leads us to a broader and more generalized formulation of brain electrodynamics in higher-dimensional spaces. Research suggests that neurons may not only conduct electrical impulses, but also emit coherent light. This biophoton emission has been hypothesized to play a role in neural communication, information processing, and even consciousness. A critical component in this formulation is the Dirac equation, which governs relativistic quantum field for fermionic particles. When applied to the brain's biophoton interactions, it suggests that photons exhibit particle-wave duality and can form coherent quantum states. The Lagrangian formulation of QED provides a mathematical foundation for understanding these interactions, describing the dynamics of electromagnetic potentials and the coupling of distributions and biophoton emissions. Additionally, the gauge field approach in QED plays a crucial role in understanding the interaction between neurons and biophoton dynamics. The brain's electromagnetic interactions can be viewed through the lens of gauge symmetry, where biophotons mediate information transfer in a manner analogous to gauge field theory. This suggests that neural communication could involve quantum field interactions beyond classical electromagnetic waves. Recent studies, such as those by Liu, Chen, and Ao, 2024, propose that entangled biphotons in myelin sheaths could contribute to information transfer in the brain, much like quantum computers' qubits for superior computational efficiency. Thus, by combining classical electromagnetism, full-wave modeling, and quantum electrodynamics, we may begin to unravel a deeper understanding of the brain's electromagnetic and quantum nature. Finally, we address the brain's ability to emit and receive electromagnetic waves, introducing biophotons as a potential quantum communication mechanism. Neurons may act as QED radiators, emitting weak light pulses. Entangled biophotons could enable quantum-like neural communication. This brings us to the final discussion: how QED may redefine brain function beyond classical models. By incorporating biphoton interactions into the total brain, we explore a framework where neurons act as QED radiators, emitting weak light pulses that could enable quantum-like neural communication. This suggests that the brain operates as a hybrid quantum classical system, where information is encoded both in classical electromagnetic waves and quantum entanglement. To fully formalize the concept of electromagnetic consciousness, we turn to a rigorous mathematical representation grounded in field theory. The brain's total electromagnetic field can be described using a modified Lagrangian density, incorporating the standard Maxwell term for classical electromagnetism, additional interaction terms for quantum electrodynamics, and a nonlinear term representing biophoton interactions, where f mu is the electromagnetic field tensor, psi represents the quantum wave function of biophotons, and lambda, phi, ℏ introduces self-interaction terms relevant to nonlinear biophoton coupling. The coupling between neuronal charge distributions and biophoton expressed via a gauge covariant derivative, ensuring local gauge symmetry. D mu equals del mu plus IEA mu. This formulation unifies classical and quantum electrodynamics, providing a comprehensive description of how electromagnetic fields interact with neural structures. Additionally, by incorporating entanglement entropy as a neural biophoton dynamics, we can explore information-theoretic principles underlying consciousness. This suggests that consciousness may emerge as a macroscopic quantum state, stabilized by long-range electromagnetic correlations in the brain. As research in this field continues to evolve, we may be on the brink of a revolutionary paradigm shift in neuroscience, unlocking the fundamental nature of cognition and perception through the lens of quantum electrodynamics. This presentation explored the brain through the lens of classical and quantum electrodynamics, highlighting its role as an electromagnetic conductor, field generator, and potential quantum system. This interdisciplinary perspective may unlock new insights into neural communication, cognition, and consciousness, paving the way for a paradigm shift in physics. Thank you for your attention. I welcome any questions.